I guess we should start. Well, thank you for being here once again. This is part 2 of this tutorial series. So last week we discussed a bit of the background in general, Flexodeal and Flexodeal Lite in particular. Today we're going to be working with Flexodeal, like the full version of it. There's a lot that I need to cover, so we just go through it, and maybe we'll have something left for the next tutorial, but we'll see. Because I think these things are important. We shouldn't rush through them. So very briefly, we discussed this already. I found out that if you just put Flexodeal in Google, you already start getting the Gemini and ChatGPT results. So yet another description of what we do. And as I mentioned last week, Flexodeal comes in 2 versions, so Flexodeal Lite and the full version. Today, we're going to be working with this one. So there's 2 parts for today. There's 2 main goals. So the first one is to study the default experiment Flexodeal, just like what we did for Flexodeal Lite. And the second part is to understand how to set up an experiment with an MRI-derived geometry, right? So we're not going to have our standard geometry or the default one. Right. So let's begin with the default experiment, and for that, let's get this version of Flexodeal. So let me see. There we go. So I'm just gonna open a terminal and go to some directory. I tend to keep a sandbox folder just in my home directory where I can put stuff that I can delete later. So I'm just going to go there. And then I'm going to write these commands, right? So we're going to clone first Flexodeal. github.com/sfusionml Flexodeal.git. Right, and for this I'm just using the public address, right? Last week we downloaded a release of Flexodeal Lite. It's up to you how you get it, right? In the third tutorial we're going to discuss more about these differences, but whether you download a release or you just clone the repository, 99.9% of the times you're getting the latest version. Right. So I have a Flexodeal folder there. Just gonna go there. So I have my typical set of files, and I'm just going to CMake this. So same thing we did for Flexodeal Lite, basically. Yes, there, and that's where my version of DL2 is. Then I can call make, so I get the executable. And for Flexodeal, it does take a little bit longer, right? Because in general, it's heavier code, it's longer, so, but it shouldn't take too long. So there we go. It says that there was a target built. And again, I have my Flexodeal executable right here, which I'm just going to run it for now, and we'll go over the details. You just let it run. It should take between 2 and 4 minutes to run, I would say. Maybe 5, depending on your machine. So far, so good? Okay. And by the end of this tutorial, or maybe next week, we're going to go over the details of what we see in the monitor, right? Because now there's a bunch of stuff, just computing. We'll go over those details. So while that runs, let's look at the geometry here. So in this case, for Flexodeal, the default geometry, so the one that you get from your C++ file, It's something that resembles the dimensions of a gastrocnemius. We're going to have now muscle tissue and 2 layers of aponeurosis, top and bottom. So the top one would be like the 3D view, like the mesh. And there are some parameters that we can use here to describe this geometry. Now, of course, because it's no longer a cuboid, we have more parameters, right? So we're going to have muscle length. There we go. Muscle length. The length of the aponeurosis now is also a parameter. The height or the thickness of the aponeurosis, the muscle width, and the pination angle, which is with respect to the line of action, right? And remember that the line of action is hard-coded to the x-axis, right? So the vector 1, 0, 0. Of course, you also have more parameters here, like this LF here, this other angle, but those are parameters that you can derive from these ones, right? How? It's just basic trigonometric identities. This is all like law of science, basically. Parameters such as the angle between the fibers and the aponeurosis, that one, right? So if you give me the length of the aponeurosis, the length of the muscle, the pination angle, I can compute that angle. The initial fiber length, right? Well, it can be computed like that. Again, law of science. And now the initial fiber orientation field is no longer constant throughout, right? So you're going to have a set of orientation for muscle fibers, which would be the gray area here, and a set of orientations for the aponeurosis fibers. And you can see the orientations here, right? So the vectors point upwards for the fibers and then downwards for the aponeurosis fibers, right? And again, once you decide what parameters to use, right? These ones, the fiber orientation, the initial fiber length, and the angle between fibers and aponeurosis, that's computed automatically, right? And then finally, we have some boundary ADs. 0 would be a fixed boundary, so no displacement there. 1 would be a moving boundary where we're going to prescribe the strain. And then all other phases, 2 through 7, are going to be traction-free phases. And that's what these numbers mean here, right? Now, in terms of the parameters file, it's pretty much the same thing as in Flexodeal Lite, but it's not exactly the same thing, so you can't use them interchangeably, right? Because the geometry is described differently, right? In Flexodeal Lite, you only need muscle length, muscle height, muscle width, but of course now you have aponeurosis and other angles too, so it's a little bit different, and we can open that here. Let me go to my sandbox folder here. So this is the repository that we just cloned, and most of the difference in this file come from this section, right? So the geometry section, just because you have different parameters. Everything else, the linear solver, materials. Of course, you're going to have more constants because now we can consider tendon and aponeurosis. So those material properties are going to be defined here too, at least the constants, right? But then nonlinear solver, the time section, which you're probably going to modify at some point, that all stays the same. Now, in terms of the boundary strain and activation files, last week we discussed how Flexodeal reads these curves by linear interpolation. So if you want to construct more involved curves, right, like this sinusoidal wave or this kind of things, you just add more points, right, and then will be connected by lines. These two files in particular were generated with a MATLAB script that is in the Flexodeal folder too. So if you want to have a look at it. And the activation was computed using a transfer function. So there's a little ODE solved there. But again, you can do it in MATLAB, you can do it in Python too. Any of those two work, right? Any questions so far? Now, in terms of the visualization, again, it's pretty much like last week. Both in Flexodeal and Flexodeal Lite, we have the same outputs in terms of like CSV files and ParaView files. One thing that I tried to do was to visualize the orientation field muscle fibers, right? That didn't work. I think I pressed the wrong button last week, basically. So I'm gonna do that now. But basically the instructions are here, and we are gonna be using this Steam Tracer tool, which is that little button there. So let me just quickly grab my mouse here. Because, well, my solver is done. And if you were running this, hopefully it's done too. And we have that folder by default, which is the one we just got now. So I'm going to go to ParaView now. And just open these files. So I was working in my sandbox folder. And this is the folder we just that just got created. I'm going to open the stretch VTU file. Just going to maximize this for now. So that's my geometry. Just going to plot the stretch field here just to visualize it for now. So it's just a cyclic contraction, right? Now, if we want to view the orientation field as streamlines, well, and remember, the magnitude of the orientation field is exactly the stretch, right? So they should match. So I'm going to go to this button here, Stream Tracer. The default option is to do a line, but if you do a line, then you're going to get like just lines that cross that line in just one plane, right? We don't want that. We want more than that. So I'm going to change the seed type to point cloud. Now notice this little sphere here. So in order to capture lines from end to end of the muscle, we need to increase the radius of the sphere. Let's do, I think it was like 12, maybe 13. It's more or less double the muscle length. Right? Whatever muscle length you have in the parameters file, double, or actually half that. Half that would be the radius. That should be enough. Now in terms of points, we need to give a lot of points here. Let me try with 20,000 first. And you always have to test this because if you have too few points, then you're not going to see a lot of lines. But if you have too many points, then you're going to clog your RAM memory, right? So there we go. And I can just remove this view for now. So there you start seeing some lines that you can interpret as muscle fibers, right? Of course, they're non-muscle fibers because we have an infinite amount of them. But for visualization purposes, this is sufficient, right? And then just want to see the play button here, right? And then you can just just ignore that warning there. And of course, if you increase the number of points, let's do 40,000. They're just going to get more lines, right? Again, there's a lot of things that you can do with ParaView. It's up to you what to do. This is just one of the ways I personally use to visualize like muscle fibers. Any questions so far? And notice that another thing is that, of course, this experiment is kind of like the default. I'm not saying that this experiment is like fully resolved, right? Because you can see like the stretch in the aponeurosis is quite large, actually. It's almost like 10%. So yeah, feel free to play around with this experiment, finding the best parameters. Maybe you need a more refined mesh. If you really need a resolved experiment now for this one, right? Of course, if you add more cells, if you increase the complexity of the model, it will run more slowly, right? So yeah, don't think that this is like the final product, okay? This is just like a default experiment, just a program of how to put things together. Any questions before we move on to the next part? Cool. All right. So that's the default experiment. When you run Flexodeal, right, because you compile this C++ file, this is the mesh that you will get, right? And there's a function called makeGrid inside that C++ code that creates this, right? If you want to use a different mesh, you can do so. And we're just gonna discuss how, okay? So for this, I've already put together some things. So let's clone this repository now. So this is the Flexodeal tutorials repository where the slides are, by the way. So I'm just going to go back to my sandbox folder and call these commands here. So the first thing is I'm going to clone the repository again. And remember, this is different than Flexodeal. This is just a different tutorials repository. So github.com and Flexodeal tutorials. So I can see that now I have my Flexodeal tutorials folder. I can go there. I have a bunch of files here. Of course, I have the slides, and then this folder, MRI experiment, which is the one that we're going to be working with. Now, there are some more things inside that folder. In particular, there are some submodules, which we need to update. And there's in particular a copy of Flexodeal inside this folder, right, that I linked as a submodule. That's why we need to do this extra step here. And now I'm just going to go to this folder, experiment. So what do we have here? We have a copy of Flexodeal. I'm going to talk about this tool in a minute. I have a preprocessor folder. And then some parameters. So I have an activation file, parameters, strain, and the mesh that I'm going to start with. Now, typically, when you get a mesh, especially if it's not a mesh that you did, right? You may not know if the mesh is compatible with Flexodeal right away, right? Chances are it will not be, right? So some pre-processing might be needed. And we can assume that we start with this mesh here, this medial gastrocnemius, left medial gastrocnemius mesh, right? Like I said here, before setting up any Flexodeal experiment, you should be aware of some characteristics of your geometry, such as the mesh orientation in units, particularly what's the line of action, right? Is it aligned with the x-axis? Is it aligned with the z-axis, right? Material IDs, right? Which, by the way, a mesh file, maybe I can do that quickly here. Let me open this folder here. A .msh file is just a text file that has vertices, connectivity information, but also has material IDs. So each voxel has a material ID, which we can understand as a tissue ID. So that tells me whether it's muscle, tendon, or aponeurosis, basically, right? More often than not, that distinction is not made when you're meshing, right? So you might have only one material ID when you need 2 or 3, right? And also boundary IDs, right? Boundary IDs need to be set so that they're compatible with Flexodeal. Now, how to view these mesh files, it can be tricky because I think the main thing is that, sure, we have Gmesh, which you can use to view these files. But what has happened to me a few times is that Gmesh has troubles with the ID 0. For Gmesh, all IDs has to be 1 and above, right? So if you have, say, a surface or a boundary that has ID 0, you won't be able to see that in Gmesh. There's another tool called Exolab that you can use to view your mesh, but you can't see any tissue ID or boundary ID information. So to solve this, I just created this little tool called MSH to VTK, so mesh to ParaView, so that we can view these meshes in ParaView, right? So we can create these VTU files. And in particular, view the tissue IDs and the boundary IDs that are set. So let's use that tool. I'm going to go back to my terminal here. And I'm going to navigate to my MSH2 VTK folder. And this is pretty much like a separate CMake project. Separate from Flexodeal, separate from the other one, the preprocessor tool. So this one is compiled separately, and the way to compile this one is a bit simpler. You just call make and the directory from for DL2, because it's also a DL2 based tool. Oh, points there. There we go. So it's compiling, it's creating the executable. And now I'm going to create these VTU files. So I'm going to call my executable here, msh2vtk, with one mesh, well, the one that I had before. And this one is in the parent directory, so just one directory up, and that's why I add the 2 dots there. Left.msh. So I read my mesh, and I created 2 files, mgleft tissueid.vtu and boundaryid.vtu. So let's have a look at those files. Let me just close this. So there we go. So tissue ID and boundary ID. I'm just going to open both. The first thing that I'm going to do here, I'm just going to increase the size of this axis here. So you can all see this, right? There we go. So yeah, I'm going to view the tissue ID file first. There's only one field here, tissue ID. So according to this color scheme, there's only one tissue ID. Everything is one, so muscle tissue, right? But notice how it is aligned with the z-axis, right? For the most part, right? And we need to decide, because the thing is that in Flexodeal by default we're going to pull our muscle along the x-axis, right? So if I want to if I put this mesh right into Flexodeal, then it's going to start pulling in pretty much this direction, right? Which is not what I want. I need to pull from the end, right? That means that I have to transform this mesh, right? I have to rotate it, I have to align it, and I have to also design the line of action, because I don't have it precisely, right? So in this case, what I'm doing is to take the 2 furthest points, which I can hand select pretty much, right? So I have a tool here that I can use to visualize point information, like that. I hand select them, and then I take the vector. So the difference between those 2 points will give me a vector, which is what I consider my line of action. And then I'm going to align that line of action with the x-axis. So I need to rotate that vector, and with that, I will rotate my entire mesh. And that's what the preprocessor tool does. Oh, and by the way, for the boundary IDs, there's also work that we need to do. because all the boundary IDs have, all faces have boundary ID 0. And if you remember from Flexodeal Lite and from the default experiment in Flexodeal, 0 is the fixed boundary. If you activate this, the muscle is not going to bulge, right? So your simulation will crash in just a couple of time steps. So that's why we need to pre-process this. Let me just close this and go back in. All right, so this is what I mentioned. Oh, and this is another thing, right? Let me plot for this box here. Where was this? So you can see here the limits for the original mesh. You can tell from this that your mesh is in millimeters. It's not in meters, right? Because there's no way we're talking about a muscle that is 200 meters long, right? So that's another thing that you need to do. You need to scale your mesh, right? And this is the important thing. You should aim to solve these differences before you input your mesh into Flexodeal, right? So you need to be aware of all these properties. Otherwise, you may put this in Flexodeal and then not know why your code is crashing. So let's use this preprocessor tool. And before that, let me just quickly open it here. So in the preprocessor folder, I have this C++ file. And I'm not going to go into a whole lot of detail. It's documented. You can read on your own. But basically, in the main function is where we have the main things that we're doing, right? So we are first reading the mesh, then aligning the line of action with the x-axis, then scale it. We are tagging the boundaries, and then we write the output. In particular, to tag the boundaries, which is this function here. Basically, what I'm doing is first computing the muscle length, right? Because I don't have that right away. You might have it separately, but from the mesh itself, I can't see right away what's the muscle length. So I have to compute it somehow. At this point, I'm assuming that my mesh has been rotated, scaled, and it's already aligned with the x-axis. So I'm just looking at the x components for each point, right? Taking the furthest x points, and that's going to give me my muscle length. And then what I'm saying here is that the first 9% of the faces, right, in the x direction, so the first 9% or the first 9% portion of muscle is going to be fixed. It's going to have the boundary ID equals 0. And then the last 2% is going to have a boundary ID 1. Because that's what I'm going to be pulling. Everything else will have boundary D2, which is what I have here. So these are the kind of decisions that you have to make when pre-processing your mesh, right? Because it's not information that we have readily available. The cut between tendon and muscle is not clear, right? So you have to decide it, right? Any questions, by the way? Any questions here? And again, I encourage you to go over the details here, just to see what are all the angles that are being computed. And yeah, this is, by the way, a tool that will only work for this mesh, right? Because this mesh is different. You may use this structure for other meshes, right? But if you just change, say, the name here of your mesh, just use a different one, it may not work, right? And it probably won't work because there's a lot of parameters that are hard-coded here. Again, it's a relatively short piece of code, but I expect to do these kind of things when you're working with meshes that are not the standard ones. Just gonna go back to the presentation here and let's compile this thing. So I'm gonna go back to the background folder and then to a preprocessor folder. So I have my C++ file there. And this one is compiled pretty much like Flexodeal, right? CMake build type release. They're going to call it make here. So because the mesh was in the parent folder, I have to go back one level, right? Where was this? There you go. Where did this go? Oh, I haven't called the preprocessor. That's what I forgot. So I called make, but I didn't actually call the executable. So let me go back to this folder and call it preprocessor. There we go. So just some numbers here. Before scaling, of course, the units are not there because I don't know a priori what the units are. But now that we saw the mesh, the units that are for volume are in millimeters, right? Cubic millimeters, I guess. And then after scaling, of course, you expect to have everything in SI units, just like meters and kilograms. So. And then I get the muscle length. Where am I going to use this muscle length? In the parameters file, right? So the parameters file is already constructed, but when you're starting to modify it from scratch, that's your muscle length that you're going to have to put there. So it's good to keep it in mind. And now just going to go back one folder. And now I have two meshes. I have mg_left, which is the original one, and then I'm going to have the transformed one. That's the one I'm going to use. And we can quickly create these VTU files to view it. Just going to go to the MSH2VTK tool and just call it here, MSH2VTK. Again, the mesh is in the parent folder, so I use the two dots here. MSH. So now that I generated these VTU files, just going to delete this and open these files. So now I have two. So mgleft transform boundary ID and tissue ID. For tissue IDs, we didn't have to modify anything. Everything is still muscle, but of course you may want to pick some cells as, choose some cells as tendon. That's up to you. For this example, just setting everything to be muscle. Where's my fill here? Right, so tissue ID, everything is muscle tissue. It's now aligned with the x-axis, as you can see. And then in terms of boundary IDs, you have three, right? So the blue one would be 0, the gray one would be 1, and then the red one would be 2, right? So you're fixing this end, pulling from this other end, then the other ones are just traction free. Any questions? So notice that here we haven't touched Flexodeal at all, right? This is just pre-processing the mesh, setting things up so that it runs properly, right? So that's one thing, the mesh, that you have to align it with the x-axis for now, right? The second bit that requires some work is setting up the quadrature point file. And that's what makes it different from, that's the main difference from Flexodeal Line. In Flexodeal Line, you don't need this file, right? But here you do. Now, what are quadrature points in general? Why are we talking about this file? So quadrature points or integration points. These are special points placed inside each voxel where Flexodeal evaluates the physics of the muscle, right? And if you know anything about finite elements, quadrature points are used in my quadrature rules to compute my integrals. That's where they come from. In particular, Flexodeal uses a Gaussian quadrature rule, and the rule's order is set in the parameters file. It's currently set to 5, and I haven't modified it. You might not need to modify it. Now, I know that I drew some like 2D figures, but think of this as like 3D figures, right? So like cubes and or voxels, right? Basically, your quadrature rules fix the location of these points in a unit or like standard voxel, like the unit cube, right? And then we use transformations to map these quadrature points and the voxel itself, the standard voxel, to the deformed one. Say like if you have like a corner one in the mesh here or one inside. It's all just affine transformations, right? So then the quadrature point file will list these orange dots here, right? In the deformed voxels, I should say. And they are listed in a predefined order, and that's very important. This quadrature file is ordered. If it has, you may have the same quadrature points, but if they are not in the correct order, Flexodeal will not like that, right? So the quadrature point file contains the ordered list of all quadrature points in the mesh. And pretty much what we get first is the location of these quadrature points. So X, Y, and Z coordinates. But this file, you can also view it as a table, right? The table that needs to be populated with other columns, such as the tissue ID, because if you have, say, muscle, tissue, and tendon, some quadrature points are going to have a tendon ID, while others will have a muscle tissue ID, right? We also have the ability to add a maximum isometric stress. Maybe you want to set everything constant to 200 kilopascals. Maybe you want to do some variations inside. Muscle fiber orientation, so the vectors, right? X, Y, and Z components. And then the fat fraction. And fat fraction is just a value between 0 and 1. Now, we need to generate this file, and we need to fill it out. So both things, or at least the first one you can do it Flexodeal. For the second one, there's a little tool that we can use there. So let's see. So I'm going to go back one level here. I want to get to the Flexodeal folder. And that's just a copy of Flexodeal, right? So I'm going to compile this the same way we compile Flexodeal Lite. Build. Oh. See, make build type, please. Sorry. Then I want to call make. And now you can start seeing that Flexodeal also has some command line arguments, and those are the ones we're going to start using now. So if you just run Flexodeal, that runs the default experiment. If you add command line arguments, then you're running something else. So I have my executable here. And the first thing I'm going to do is to generate the list of these quadrature points. How do I do that? I call Flexodeal with the mesh that I'm going to use. And again, the mesh was in the parent directory. mg-left. And I'm going to use the transform one, right? And then the flag qp list only. So for this one, just gonna run that. All it does is to generate this this file. Nothing else. Nothing else is run. You're not running the whole Flexodeal simulation, right? So if I go back one level, which is where my mesh is located, I have this file. mgleft transform dot backup dot qp dot csv. The extension doesn't matter much. I decided to just use the dot backup extension to just differentiate it, because I'm going to open this here. So that's the CSV file. It only has 4 columns, right? So X, Y, and Z locations of the quadrature points, and then the tissue ID. You need to populate this file with all the other columns, all the other material properties. So, I'm just gonna trim this. Let me go back here. So what I recommend is to, there we go. What I recommend is to make a copy of this file. Just keep it there, keep it as a backup, make a copy and modify the copy of this file. So, what did I say here? So I'm going to move this file, transform, .backup.qp.csv, and I'm going to move it to the Flexodeal folder. Or if you are in the Flexodeal folder already, you can execute the command that it's right here. Right, so I have my backup file there. And now I have to add these columns. You might be wondering why we are, you may be wondering, I don't know if you are, but like, it's a CSV file. We can open this in Excel, right? Can anyone tell me why would you not do that? What's the risk of opening the file in Excel, adding those columns, and then exporting it back to CSV? Is anyone aware of that?
If it is a very defined mesh, then in Excel you will always get you will not be able to open the file there, which loses quality points and runs into issues.
Right, that's one thing, right? If your mesh has a lot of voxels, you're gonna have a lot of quadrature points, and I think the limit is like, I think it's like 2.5 million rows or something like that, right? So that's one thing. Another thing is the fact that when you do this process of like reading in Excel and then exporting back to CSV, you might be losing some digits of accuracy, right? Because by default, CSV tends to export everything in decimal format, not in exponential format, right? So you have to be careful if you are using Excel. Personally, I don't recommend it, because if you lose some digit of accuracy, then when you're reading this file in Flexodeal, the quadrature points are not gonna match. So we have a little tool here, which is this one. It's a bash script basically that adds columns with constant values to this CSV file without opening Excel. Now the command is a little bit long, but basically the syntax is as follows. So I have my backup file there. Just gonna copy that. Let's call it mgleft transform.qp.csv. And then I'm going to call this bash script. So bash add columns to qpfile.sh. The next argument is the file that I want to modify, mgleft transform.qp.csv. And then I'm going to add the columns, right? So it's name of the column, value, name of the column, value. So that's the first one, the maximum isometric stress. Be careful. I did not raise my hand. Let me just close that. Careful with the names, right? So the names that I have here are the names that I have here. And you cannot use a different name, right? Otherwise, Flexodeal will not recognize that property. So max stress muscle 200,000, muscle fiber orientation X 0.9397. I'm assuming 20-degree pronation angle. So That one would be cosine of 20 degrees. Then muscle fiber orientation y 0. And then the z component would be sine of 20 degrees. Which is 0.3420. And then I'm just going to add 20% fat. Fat fraction 0.2. Hopefully I didn't misspell anything, because that happens. If it happens, you can go and modify the CSV file directly, because this is just the first line, right? If I go back to the Flexodeal folder, now I have my original columns and then the ones that I just added. So this one, muscle fiber orientation, X, Y, and Z, and fat fraction. Now this is a little bit cumbersome, but there's two things here. One, you need a quadrature point file for every mesh that you consider, right? Because every mesh has different quadrature points, so therefore you'll need a different quadrature point file. So that's one thing to keep in mind. Another thing to keep in mind is that this is one way to fill the table with constant values, but you don't have to, right? You can use variable values, and in that case, you can use pandas in Python to modify the CSV file or MATLAB, right? And just set it in whatever way you want. That's a flexibility, you know. It's like, yes, it's a little bit cumbersome, but you also gain flexibility in taking this approach. Any questions? So then, these are the two main things, the two main pieces of the puzzle, I should say, that we need to set up. After that, we can just run the simulation. The parameters, the strain, and the activation, they're all set already. This is from like a human experiment. Not exactly using the same muscle, like the same subject, I should say. Muscle is the same, but like subject is not, right? But this one gives us an idea of what boundary strain and activation profile look like in real life, right? So, in general, the call to Flexodeal accepts the following parameters. So, parameters, boundary strain, and activation, those were already things that we had in Flexodeal Lite. Same as the ability to modify the output directory, but of course now we have a mesh file, quadrature point file, and then this list of quadrature points, right? Which is the one we just used. So, to run this experiment, we will need to use pretty much all these options. Let's see. So Flexodeal, select my mesh file, and for this, keep in mind where you are in terms of directories, right? So the mesh file, the parameters, the strain, and the activation are in the parent directory, whereas the quadrature point file is in the current directory, right? That's why some of these arguments have the 2 dots and some others don't. Left transform message qp file. Left transformed.qp.csv. Parameters. Left parameters.prm. Boundary strain. Activation. And let's call the output directory results MRI. and we can run it. If this doesn't work right away, Flexodeal has some. Will tell you what you missed, basically. Well, there we go. So something is running in the background, and of course, this is this is like the cooking show where I show you the recipe, but I already baked the cake. So of course, I already ran this because it takes some time, right? And in fact, this simulation in one of the computers in the lab took about 5 hours, right? So just keep it running, but don't expect that this will be done now. So once you have that, then I just got a video of the displacement magnitude here. So of course you can see that like the bulging, the deformation is not uniform throughout the muscle, right? But of course now you have access to all the fiber orientations, the stretch, strain rate, velocities, pressure, dilatation, all these fields to view them as part of your files, but also forces, energies, everything that is in the CSV files, right? Any questions? Any questions at this point? If not, there's the last thing that we need to discuss. And it's a good thing that this will run because now I can tell you what this means, right? So both in Flexodeal Lite and Flexodeal, when you run the code, you'll have a bunch of outputs, right? If your code is it's very light and your mesh is very coarse, like these lines will go very fast, right? But if not, if you have a more complete experiment like the one we are running now, it gives you some time to read what's going on, right? Now, what information do you have here? At the beginning, you have some information about your geometry, your mesh, how many voxels or cells you're taking here, markers to track displacements if you're using any, some information about the numerical solver, right? We're using direct or conjugate grading or any other solver. Whether your contraction is dynamic or quasi-static. Then energies and forces at the current time step. So you're going to have energies here. This is the first time step. That's why they're all 0, right? And then forces. So this is the vector magnitude at each boundary ID at the current time step. So in this case, this terminal output came from Flexodeal Lite. So we had the cuboid with 6 faces with IDs 0 to 5. So those are the IDs, and then these are the components of your force. And of course, these energies and forces are available at each time step. They're also in CSV files. This is just for monitoring. Now, the main thing here is to look at this kind of table here, which is the one that has been the one that you get at almost every, the one that you get at every time step, right? So 0, 1, 2, 3, and 4 here refer to the nonlinear iterations, right? In this case, we use 1, 2, 3, 4 nonlinear iterations for this time step, right? Typically, the more activation you have, or the higher your activation is, the more nonlinear iterations it will take to solve per time step, right? In this case, we're using a direct solve, meaning that we're using something like Gaussian elimination to solve the linear system. So that's exact, quote unquote, just one iteration, one linear iteration. And then we have some columns here. The first 4, the ones that start with res, they tell me about the norm of the residual vector, right? So we're solving the equation in the end, r equals 0, right? Residual, you have all your forces there, all your integral terms. So when you write as a vector, after discretization, everything, that's your norm. Rest U would be the norm of the displacement block. Norm P would be the pressure block, and then rest J would be the norm of the dilatation block. Then nu here, these last four columns, they refer to the neutron increment, right? When you're done solving your nonlinear part, your increments will be 0, right? So of course they have to decrease. But notice that these are just absolute norms. So you can see that nu u here decreases to 10 to the minus 7. I think by default we're setting this to like 10 to the minus 4 or 6, something like that, right? P goes down to like 1, and then the dilatation goes to like 10 to the minus 7. But the pressure, remember that pressure is in the scale of kilopascals, right? So a difference of 1 pascal is not much, right? If your pressure is like 100, 150,000, something like that, right? So convergence is achieved when this column here, rest U, falls below tolerance force, which is something that you said in the parameters file. And then nu U, and you have convergence with this one falls below tolerance force, and nu U falls below tolerance displacement. And these tolerances are set in the parameters file. Any questions about this? So in this case, you see that rest U is just pretty much going down, which is what we want. Nu U also is going down, which is also what we want, right? Once these residuals are not or don't start going down, that's when we get worried, and then we get divergence, and then our solver crashes, right? And then we have to figure out what happened, right? Below we have some errors. In particular, the one that I like to look at is the change in volume, right? Let's see what's the change in volume here. So not much, right? No change in volume yet. Sometimes it gets to like 7%, maybe 4%. Sorry, 0.7%, 0.4%, right? We always try to keep things under 1%, right? So in this case, there's no noticeable change of volume. And then the energies and forces are updated RH times 7. And at the end, you get your summary with the amount of time that you spend in each task, right? And again, the experiment that we're running now, this one will take about 5 hours, so we'll not finish here. Any questions? So this is the main thing. Yeah, this is what I wanted to show today, and I'm glad we made it to the end. So now you have Flexodeal and Flexodeal Lite to play with, and again, all the parameters, everything is in this Flexodeal tutorials repo. So clone it again, just study in detail at home. And if you have any questions, like feel free to send me an email. Again, you can go to the DL2 website to learn more about DL2. There are papers. And part of my thesis too, where we talk more about this this framework, and also you have ParaView, because again, ParaView is a really powerful tool to visualize things. So you can create really beautiful things there. So yeah, pay attention to that. So yeah, I think we can end the tutorial here.